तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
I am going to give a set of lectures on mechanical measurements. The lectures are arranged in modular form, and today we will just introduce the module number 1, and we will see what are the things we are going to cover in this module. The first topic which I am going to cover is to introduce the area of measurements, and mechanical measurements is a sort of a subset of what we can call as measurements. Therefore, introduction to measurements will be a general description of what measurement means, and then of course we will also look at what mechanical measurements are later on. When you do any measurement in whatever field it is, the measurement process is prone to some errors, and even before we start looking at the specific measurements and how we do it and so on, it is good and necessary to understand about these errors, how to either minimize them or to characterize them and so on. So, the errors in measurement forms the topic which will be given emphasis to start with, and when we talk about errors, there are some statistical principles which are required to understand the nature of errors, and of course when we go into the specific topic we will give more details. Right now it is sufficient to understand that there are some statistical principles involved in the characterization of errors, and that will be the topic which we are going to look at. When once we have made or performed a set of measurements in whatever field it is, one would like to look at the data in the form of a summary, and when we want to communicate it to somebody, we should be able to tell him or her what exactly is the role of this measurement, what it has achieved in terms of what is useful to the person who is going to look at that. So, regression analysis is a natural thing to do. Regression analysis tries to put everything in the form of a simple formula or a simple set of formulae which will be useful to the user. Instead of going through the various measurements we have performed and understanding them, one can simply go to the results in the form of a regression analysis and look at that, and that will give us information about what the experiments have achieved. When we talk about regression analysis, naturally we would like to look at what is called correlation, or the relations existing between different quantities which we have measured, and to understand whether these correlations are good or bad, whether the correlations are really not an artifact which has come out of our faulty understanding of what has happened, whether it is proper to do the way we have done the regression analysis and so on. This is understood by looking at what is called a correlation. The next topic which we will look at in this module 1 will be estimation of uncertainty, and this will be followed by a good presentation of data in what we call as a good presentation of data. Good presentation means it must be understood by the user without coming to the person who has made the work. So, he must be able to understand what has been achieved without the help of anybody. So, it should the work should speak for itself. Therefore, the presentation of data is a very important part of this process. And the last topic in the module number 1 would be the design of experiments. We will talk about how to conduct the experiments, whatever may be the type of experiment we are going to do, how to organize the different instruments, how to look for the proper instruments to be used for the measurement in the particular experiment we may have in mind, then how many data to collect, what kind of variations or ranges of data we should have, and so on and so forth. This is what will be the final part of this module 1, which will be on the design of experiments. With this overview, I am going to the first lecture in this series, which is just an introduction to the study of mechanical measurements. Measurements can be classified according to the field in which we are going to be working. Electrical measurements, of course, describe measurements in electrical engineering or electrical sciences. Measurements in physics or physical sciences have their own flavor. Measurements in biological sciences, they have their own flavor, and so on. And mechanical measurements pertain to measurements which we undertake in mechanical engineering to describe various systems which we meet with in practice. There may be thermal system, there may be mechanical system involving measurement of length and velocity, acceleration, and so on. It could be thermal, for example, temperature measurement, pressure measurement, anything which has to do with the thermodynamic characterization or thermal characterization of systems, which will come under that category. And then, of course, measurements which may be, there are various ways of classifying measurement, which will of course come to as we go along. So this slide shows the need for measurements. I am trying to make out a case for why we want to measure. So there are several reasons why one would like to make measurements. So the central question is why we want to measure. There are, in my opinion, there may be many other reasons depending on who is going to talk about it. In my view, there are two important reasons and a third reason which I am not going to give much importance, and let me just go through the reasons. One is to generate data for design, because engineering and mechanical engineering is mostly concerns itself with making of things, design of things, and then making of things or manufacturing the things. And in this, a lot of information is required in the form of data regarding the mechanical behavior, thermal behavior, and other behavior of the system under consideration. Whatever we are designing requires a lot of data to support the design activity. That is one of the most important things, and therefore I will concentrate on generation of data for design as one of the most important aspects of why we want to measure. The second and more basic reason why measurement is undertaken is to generate data to validate. That means if there already a theory is proposed or existing, to validate the theory we require a set of data to be collected, an experiment should be to be performed, and we want to validate the theory. Either validate, or of course we can also have an experiment which may show that the theory is not valid. So validation of a theory which is proposed either by you or by somebody else, that is one reason why we want to generate data by doing some experiments. The second one is to propose a theory based on a set of measurements. Actually, if we go back and go through the growth of science, modern science developed as an experimental activity. Science is the scientific method itself means conducting experiments, then making some theoretical framework, and then finding out whether the theory is going to be valid in all cases, and then if it is not valid, then refine the theory so that it can be made to be valid for different cases which we may have not understood earlier, and in other words to make predictions based on the theoretical framework. And to validate these, again we go back to the experimental method, and therefore the scientific method and the experimental method are one and the same. So generate data to validate or propose a theory is one of the most important activities and which is required for the growth of science. There is a third aspect which is also very important, and this is measurement for commerce. We are quite aware that whenever we go to a shop or whenever we go out and buy something, the commodity which we measure or which we buy is going to have some measurements. Either it may be a certain length of a piece of cloth, the width of a piece of cloth, or it could be a volume of some material like petrol or oil and so on. So we would like to make as accurate a measurement as possible of these quantities. So commercial aspects also sometimes play a role as to what kind of measurement method we are going to use, how accurately the measurement has to be made, and so on and so forth. So the three important measurement reasons for making measurements are: one, generate data for design; number two, generate data to validate or propose a theory; and number three is for commerce. And in this set of lectures we will be interested only in the first two, that means generated data for design and generate data to validate or propose a theory. So, with that brief idea about why we carry out measurements, let us look at the categories of measurements. In fact, there may be different people might put it in different ways. I am going to just give a possible way of categorizing the measurements. So, there are in fact only two major categories. One we call as the primary quantity, which is shown in the slide, and a second one I call as the derived quantity. I will describe more fully in a moment. This is regarding the quantity we are going to measure in our experimental process or in a measurement process. Primary quantity, for example, I can think in terms of temperature of a system or length of an object. This is the primary measurement which can be done possibly using a single instrument. For example, time, I am going to use a clock and I make the measurement. There is nothing more to it, there is no division possible. Time is the measured quantity and there is only one quantity I am going to talk about when I am making the measurement of time or time duration of a process. However, when we talk about the derived quantity will assimilate into itself several different measurements. As example, I can give, for example, velocity. Velocity is the distance travelled by a certain moving object divided by the time it has taken to cover that particular length of travel. So, the derived quantity requires at least two measurements. One, the measurement of the distance between the 2 points which has been covered by the moving object, and then of course, the time it has taken for this particular action or activity. So, derived quantity is obtained as a ratio of two measurements. So, in other words, we have a primary measurement of the distance travelled, another primary measurement of the time duration for which this activity took place, and to obtain the derived quantity I have to use it as I have to get it as a ratio of these two quantities. Of course, it is just a very simple example I have taken. The ratio of two quantities is going to give a derived quantity. Many times it may be a more complex formula which relates the derived quantity to the quantities which we are going to measure. The primary quantities may be involved, sometimes to the power, sometimes the logarithm of that quantity, and so on and so forth. So, people who have some idea about measurements will understand that primary quantity and derived quantity are related to each other. The primary quantity is the primary measurement or the measurement of one thing at a time using one instrument maybe, and whereas the derived quantity requires the putting together of various measurements of primary quantities according to some formula. So, this is one way of categorizing the measurement as primary and the derived quantities. In fact, we are going to use this theme of primary measurement or primary quantity measurement and a derived quantity measurement throughout the set of lectures which we are going to give on mechanical measurements. Sometimes we also look at the method of measurement as either a probe method or the intrusive. That means that we are going to put an instrument into the measuring process, something which you are measuring. We are going to introduce an instrument right into the system, and then of course, the probe will to some extent, even if it is very small, it is going to disturb the system, and assuming the disturbance is very small, we will try to make the measurement. So, the intrusive measurement of course is easier to do, sometimes many times it is cheaper than the non-intrusive type. The non-intrusive type requires a lot more of money to be spent on the method of measurement, the instrument and so on, but the non-intrusive, if it is truly non-intrusive, it is not going to affect the measured quantity. Of course, in a very basic way, any measurement will to some extent intrude with the system about which we want to understand and what we are going to measure. It is a very philosophical question, but here we are talking about in a very restricted way. So, the intrusive certainly requires, for example, you want to measure the temperature of a bath of water, you have to put a thermometer into it, and of course, the thermometer is going to interact with the system, the bath of water, and it will disturb the temperature right close to the thermometer, therefore, to some extent it is going to affect the measurement. Whereas, if you are using a laser beam, Of course, laser beam also to a very small extent maybe it will intrude, but it is more non-intrusive than compared to a thermometer which you want to introduce into the system. So, just to understand what we have mentioned in the previous slide, let us look at a few examples. One is we talked about the measurement of a primary quantity like for example, temperature, presumably it can be measured using a single instrument or a very simple instrument like a thermometer. Another example would be the measurement of power. Let us take the example of an object which is heated, and the power can be measured using a wattmeter, temperature could be measured using a thermometer, suppose we want to look at the process of heat transfer. We measure the temperature of the object, we measure the power which is given to the system, then the heat exchange is measured in terms of a flux which is nothing but power divided by unit area, and you will realize that power itself is a quantity which is per unit time. Therefore, when I say heat exchange process, I am talking about a flux which is the ratio of power per unit area, and the power is measured using the wattmeter, and the area has to be measured using subsidiary measurement. For example, if it is a cylindrical object, I will measure the height of the cylinder and the diameter of the cylinder. So, if I am interested in finding out the effectiveness of the heat exchange process, I would be introducing a quantity like the heat transfer coefficient. So, this example will show exactly how many different things we have to measure for obtaining this quantity called the heat transfer coefficient. We can define this as power dissipated per unit area, that is the flux, divided by the temperature difference. Between the system and the surroundings to which the heat is being transferred. So, let us use some symbols, and then in the next page I am going to show what is happening. So, if I use the heat transfer coefficient as H, this is nothing but the power dissipated per unit area, P divided by A, divided by delta T, the temperature difference. So, the quantity which I am interested in finding out, the heat transfer coefficient, requires measurement of power, one primary quantity which is being measured. Area itself may involve measurement of the height of the cylinder and the diameter as I indicated. Therefore, two measurements are going into this, and of course, here I have the temperature of the system and the temperature of the coolant, or what is taking away the heat. So, essentially if you look at this particular simple experiment of determining the heat transfer coefficient or heat transfer from a cylindrical object to a coolant which is flowing around it, I require one power measurement, two length measurements, and two temperature measurements. So, the total number of measurements total number of measurements is just the sum of all the 1, 2, 3, 4 and 5. 5 measurements are at least required. And all these 5 different measurements are of different quantities. Power is the amount of heat which is being dissipated, which may be measured in terms of the amount of heat input to the heater if it is an electrically heated object. Then the area involves the height and the diameter measurement. These are length measurements, both are lengths. They may require different instruments. The height may be measured by one instrument, and the diameter may require the measurement using, for example, a vernier caliper or something like that. And the temperature, of course, we may require different thermometers as required. So the total number of measurements is 5, and what we are going to get is one derived quantity. So to get one simple derived quantity, the heat transfer coefficient, which is normally used in heat transfer applications, I require to make at least 5 measurements to get an idea about this derived quantity. Therefore, 5 primary measurements or 5 primary quantities are measured, maybe using 5 different instruments, different types of instruments, and then they are combined together by using a simple formula like this, P by A divided by delta T. Of course, this formula seems to be very simple in this case, but there may be cases where the formula may be more complicated. Let me take one more example. Suppose I want to measure the volume of a vessel. This is also an important measurement which is required in many applications. There are several different methods. Let us just look at 1 or 2 ways of doing it. One is, of course, to measure the dimensions, measure the internal dimensions of the vessel, and using a formula to calculate the volume, and then of course use a formula. A second method, of course here we are measuring, but we are measuring the internal dimensions and then combining them using a formula. Or we can fill the volume with a liquid so fill the vessel with a liquid like water, for example, which is easily available. Then empty this into a measuring jar. So let us look at the difference between these two methods of measurement. In the first case, I am measuring the internal dimensions. If it is a spherical vessel, for example, if it is known that it is a spherical vessel, I need only one measurement, the diameter of the sphere, inner diameter of the vessel. If it is a complicated shaped object, it becomes more and more difficult to make this measurement. This is difficult to perform if the shape of the vessel is not very simple. If it is a complicated shaped vessel, it becomes more and more difficult to use this method. So the method number 1 is not necessarily the one which we are going to adopt. The method number 2 has some great advantages, because the shape of the vessel is not a very problematic thing in this case. You just fill it with water and then transfer this to a measuring jar. Measuring jar is nothing but a vessel of known shape. So whatever is occupying the vessel, whose shape may be non-uniform, which may be a complicated shaped vessel, I am going to transfer it to a vessel whose shape is very simple and straightforward, maybe there are graduations on the sides of the vessel, so that I can simply read off the volume directly from that. So, you see that these two examples are given. This example of measuring the volume of a vessel is an interesting example, because it shows how you can change the method to suit the particular measurement which we want to perform. If it is very complicated, you can reduce the complexity by going for a simplification, as I have indicated here. So, we have talked about primary and derived quantities. I have given one or two examples which indicate different types of measurements and the number of measurements required for a derived quantity obtained, and so on. I have also given some idea about how to look for a specific method which is better than another one which you may think of to start with. We will see later that the errors in measurements are linked with the number of measurements we make, and if you can find a method which requires lesser number of measurements, it is likely that the amount of error we make in the measurement or the measurement of the derived quantity will also be smaller. So, with this background, let us look at the intrusive and the non-intrusive methods slightly more in detail, and for this let me use the board. So, what I am going to do is to take one or two examples again, like we did in the case of the other two cases. Let us look at measurement of velocity. Now, I am interested in measuring the velocity, let us say, of a stream of a liquid or a fluid, of a stream of, let us say, something like air, velocity of a stream of air. There are several methods which are available for doing this, and of course, we will consider more fully when we take up the measurement of velocity in its own right. But right now, what I want to do is to show what are the different possibilities and look at probe type and a non-probe type or non-intrusive. Those of you who have had some exposure to fluid mechanics will know that velocity of a stream can be measured by converting the velocity or head or velocity to a pressure head, and for example, we can use an instrument like a Venturi meter. So, in the case of Venturi meter, what we are going to do is we are going to deliberately introduce a change in the area of the cross section of the flowing tube, and possibly we will shape it in the form of a converging diverging nozzle, and therefore, we are going to change the area of cross section and therefore, the velocity of the fluid which is flowing through that. So, when the velocity increases, when it goes through the converging part of the nozzle or venturi, the velocity will increase, and because the velocity increases, the pressure will drop. So, we measure the pressure drop across the venturi, and then we try to find out what it corresponds to in terms of the velocity. So, the Venturi meter is a probe type one, because it is going to introduce deliberately a change in the cross sectional area, and therefore, there is a change in the velocity. We are not measuring the velocity which is existing originally, but we are trying to modify the velocity to increase it and then try to measure it. And of course, in this whole process there will be some additional pressure drop. Other than the pressure drop due to the acceleration of the fluid, there will be additional pressure drop due to viscosity, and this cannot be recovered. Therefore, the probe type will certainly give you the velocity of the fluid stream, but it will also introduce some kind of a pressure drop which is a disadvantage. Suppose I use a non-intrusive method. For example, I use a laser Doppler instrument. It is considered to be non-intrusive. So, what I am going to do is I am going to use a laser beam or maybe more than one beam, make it cross, go through the medium whose velocity I want to measure, and assuming that the medium has got some dust particles, these dust particles will scatter the laser radiation, and by looking at the scattered pattern we will be able to get the velocity of the stream of air. In these two cases, the probe type which uses a venturimeter, I am going to get only the average velocity of the fluid in the tube. In the case of non-intrusive laser Doppler instrument, I can make the measurement of the velocity at any point within the flow. That means I can get more information from this. By scanning the entire cross section of the flow, I can even find out how the velocity is varying across the cross section. Therefore, not only that it is non-intrusive, it is also more productive, because it is going to give you more information about what is happening across the cross section. Of course, the non-intrusive is a relative term. We are assuming that some naturally occurring dust particles in the air are going to do the business of scattering the radiation. If not, we are going to introduce some small particles in the form of smoke, for example, and of course that will also to some extent it should interfere, but normally it is considered to be non-intrusive. The advantage of non-intrusive method is that it gives you the information without any probe, and therefore there is no external influence on the flow. Of course, you may require a window which is transparent to the radiation and so on, so you have to arrange it properly. It may be more expensive to do the non-intrusive measurement, but it can also give you more dividends in terms of better measurement, more accurate measurements possibly, and also it will give you details which the probe type measurement may not be able to give. So, with this background, let us look at a general measurement scheme. In fact, whatever we are going to cover in this slide is more or less valid universally for any measurement which one is going to make. Now, it need not necessarily be a mechanical measurement, it could be any measurement, and the principles involved are very easily, nicely brought out through this simple slide. So, any general measurement scheme must have a quantity which we identify as the measurable or a measured quantity. A quantity of interest to us which needs to be measured is the quantity which we have to focus on. The measurement focuses itself on the measurement of that quantity which is of interest to us. So, a measurement may be a direct one or it may be an indirect one. When I say direct one, you may measure the quantity directly without converting it to another form. So, when you want to convert it to another form, most of the time we want to convert it to the form of an electrical signal, not necessarily. Most of the time it is yes, many times it could be also a motion of a pointer and so on, but in general we are going to convert the measured quantity to a maybe using a transducer to another form, maybe in the form of an electrical signal, and this requires a detector which will respond to the measured quantity. For example, if I am talking about temperature measurement, I would require a detector which would respond to the change in the temperature. There must be a definite relationship between the temperature and the output of that detector. The output may be either directly an electrical output or it would be some other output which can be converted to the form of an electrical output, and therefore we require what is called a transducer. A detector and a transducer go together. The detector which responds to the measured quantity or the variation of the measured quantity, and the transducer to change it to the form of a signal which is easy to condition or to manipulate and so on and so forth. And many times the detector and transducer system may also have its own calibration or reference signal. For example, if I am measuring the temperature of an object, I may want to compensate for the variations in the temperature of the surroundings. So, what I have is a reference signal which is produced either electronically or electrically or by having another instrument, such that it is compensating the measurement which you are doing. If it is prone to any influence of the room temperature, I can produce a signal proportional to the room temperature and incorporate in the detector part of the thing. That means that I can compensate, if it varies I can compensate for the changes of that particular quantity. So, once the detector detects or measures the measured quantity in terms of an electrical signal, it can be conditioned to the required, whatever is required by the rest of the things which are shown here. For example, in the case of analog instruments, the signal is usually in the form of either a current or a voltage, and directly it is measured by using an ammeter or an voltmeter or an oscilloscope or whatever. Sometimes, however, we want to condition the signal such that it is in the digital form, because it is easier to manipulate the signal, and therefore, signal conditioner can mean many things. It could have some amplifiers, it could also have a digitizer or a to D converter, so that the signal when it comes out of the signal conditioner is in the form of electrical impulses, and this could be easily manipulated by a computer. And of course, the signal conditioner will require external power, which is shown here to accompany the signal conditioner. Once the signal is converted to the proper form, whatever is required for the measurement, it goes to the computer through an interface. Can we have a look at the slide, please? So, it goes to the computer through an interface, and the computer can do several things. The computer can take the data and manipulate further by using a software. It can make a presentation in terms of a particular, let us say on the computer screen itself we can look at the signal as it is coming in and see what is happening to it, for example, over a period of time, or it could be output in any other form, maybe in the form of a chart which is going to be taken out to a printer, or it can produce a signal, whatever signal is coming from the measured quantity here, the detector, transducer and signal conditioner. It may be used for controlling the measured quantity. Suppose we have the measurement of temperature of an oven, for example. I would like to maintain the temperature at a particular value. I can use the signal coming out of the signal conditioner and use a program and use a controller which will maybe turn on the or increase or decrease the setting of the heater and so on, so that we can control the measured quantity to the desired level. So, a general measurement scheme is what is shown here, which consists of all the components which I have indicated, and in particular some of them may be missing. For example, if we do not want to control the activity or the measured quantity, the controller may be absent. For example, if I do not want to output in the form of a chart, the printer may be absent, and so on and so forth. If there is no calibration required or the reference signal is not needed for a particular instrument, this may be absent. But in general, these are the many or various components which go to make a general measurement scheme. This may be for one particular quantity I have taken. If you have several measured quantities, you have to have a duplicity of these, for example, measured quantity 1, 2, 3, etc. There may be different detectors, different calibration signals, and they all have to go into the same signal conditioner. Maybe we will have to have a multiplexer which will get signals from various detectors in a series of readings, or it will store in one buffer, and from there it will be read into the signal conditioner in a succession, and then it will be taken to the computer, manipulated and used for either for control or output. So, the general measurement scheme can be for a single measured quantity like the temperature of a system, or it could be for measurement of several quantities simultaneously. Normally, when we set up an experiment in the laboratory, we have as we, for example, we gave some example. We made the measurement of the power, then we made the measurement of temperature of the system and the temperature of the ambient. We measured the area of surface and so on and so forth. Several different measurements are involved at the same time. Therefore, if you want to completely take care of all the signals coming from the various instruments by a central processing unit like the computer here, I would have to duplicate this part, the measured detector and the calibration. This part has to be duplicated, and then it has to be conditioned by a single processor, and that can be easily done now with the availability of fast A to D conversion, then fast computers and so on. It is even possible to do it in real time. Therefore, a general measurement scheme is for measurement of a single quantity or several quantities at the same time. So, whenever we talk about measurements, I mentioned even when I introduced the module to you, we have to think in terms of the errors which may occur in the measurement. For example, if I am talking about the measurement of several quantities A, B, C, D, etc. for a given derived quantity, all these quantities are measured by using an instrument or maybe different instruments, and each instrument has got its own problems in terms of errors, and we will have to see how these errors are going to be characterized, whether we can take care of these errors in some sense, whether we can estimate these errors. Therefore, the first issue which we have to face is the errors. The errors are always present, even with the best of the instruments, best of the measurements, you will have some errors there, and these errors may be of two types, systematic or random. So, we will take up these two cases slightly later. The other issue which obviously is very important is the repeatability of the measurement. So, if you make the measurement on one particular day and repeat the measurement after 2-3 days, or you make the measurement repeatedly one after the other, you make the measurement let us say in the morning, again set up the experiment, make the measurement in the afternoon and so on. So, repeatability means are these going to be close to each other? If the measurements made at different times are going to give you the same value, of course same value you cannot get. Are they values close to each other? Repeatability is a thing which talks about the closeness of repeated measurements. If it is not repeatable, then we have to change our method and change the experimental setup maybe. So, we have to give up the whole measurement process, because if it is not repeatable, there is no need to make the measurement. It is of no use to make the measurement. And in fact, we will show later that repeatability and the errors which I have mentioned here are to some extent are dependent on each other. They are dependent on the errors, and therefore, we will look at that a little later on. In order to circumvent some of these things like systematic errors, we are forced to use a calibration. Calibration is a process of comparing a particular instrument with an instrument which is accepted as of good quality. So, calibration means comparing an instrument X with an instrument which is already available, which is already shown to be proved to be good, and somebody has given you a certificate saying that that instrument is good. Then you compare your measurement or your instrument with the calibrated with the standard reference. Calibration can also mean comparison of the measurement using our process. Let us say I am interested in the property called thermal conductivity of material. I will measure the thermal conductivity using my apparatus and compare this value with what is obtained by somebody else using a calibrated or with a standard reference method. Or I can even use a material which we call as a standard reference material, for which I am going to obtain the thermal conductivity in my laboratory, and then compare with the value which is quoted by the standard manufacturer. The manufacturer will give you a value, then you find out the value in your laboratory, compare it. So, calibration can mean either calibrating the instrument directly with an instrument which is standard, or you can use a material for which the property has been measured and given under certificate by somebody, and then you make the measurement of the same property using the same material in your laboratory and then compare with that one. So, calibration and standards go together. Calibration either for the instrument or for the material which you are thinking of. Of course, nowadays this linearity or linearization is not a very important issue. However, in instrumentation practice, normally people talk about linear. It is best to have a linear relationship between the input and output. If you are measuring a quantity X, and if the output of the instrument is directly proportional, it is very easy, because calibration becomes a simple multiplication by a factor. But nowadays with the data acquisition systems, with the computers and so on, these have not much of an importance, and therefore, nowadays we are not bothered about linearity or non-linearity of the output. Any of them can be taken care of easily by proper signal conditioning and using the proper instruments and so on. So, let us look at in more detail about the nature of measurement errors. These errors, as we mentioned earlier, may be of two types, and I am just recapitulating them in this slide. They are prone to two types of errors. One we call as a systematic error, and the second one random error. Systematic means whatever you do, your measurement is always going to have some error. That error is systematic. That means you cannot reduce it, you cannot avoid it. If you are using a particular instrument which is having some defect, whatever measurement you make, that defect will show itself. So, if by calibration and by standardizing we can certainly reduce the systematic error or account for it or make a correction for it. So, systematic errors are those errors which can be accounted for by proper evaluation of the instrument or the process of measurement, and then we can remove that or at least reduce it to a large extent. However, if I look at the so called random errors, no such possibility exists. Random errors are not quantifiable directly in terms of a cause and effect relationship. We cannot say that the random error is because of a particular reason. Random errors occur because of unknown reasons, untraceable reasons. Therefore, what we do is we will look at these in a little more detail. Systematic errors we also refer to as bias. They are due to faulty or improperly calibrated instruments. They may be reduced or eliminated by careful choice of instrument, as I indicated just a while ago. However, if I look at the random errors, these are due to non-specific causes like natural disturbances that occur during the experiment. There may be vibration, there may be, if you are doing a heat transfer experiment for example, there may be a air movement in the room which may affect the heat transfer process, or somebody may shake the table and it may alter the readings we are going to get, and therefore, these are something which cannot be quantified, these cannot be eliminated. What we can do is to look at the characteristics of these errors in terms of a statistical analysis. We will go to the next slide. We will see that random errors have some statistical feature which characterizes it. So, the statistical analysis of the data is going to only talk about the random errors, and if you look at the systematic errors, there is no such statistical analysis possible. Statistical analysis will only apply to the random errors because they have some statistical variation in them, and we can characterize it by statistical analysis, and that is what we are going to look in a little more detail before we proceed along. So, let us look at the process of measurement, and let us see what are the qualities which we look for the measurement, and we will define two new quantities. I will call them as accuracy number 1, and number 2 I am going to talk about precision. So, the accuracy is something to do with the first type of error, the systematic error. For example, if I am measuring a particular quantity whose value is already known to me, if I am measuring a quantity whose value is already known to me from some reference or somebody has already measured it, then the systematic error or the bias will be the difference between the measurement which gave the value which I obtained in my laboratory or by using my measurement process compared to the accepted value for that problem. For example, the acceleration due to gravity g is known to be about 9.81 meter per second squared. So, suppose I make an experiment in the laboratory using a pendulum and make the measurement of the time period of the oscillation, and from that obtain the value of g. It may either come out to be 9.81 or it may be slightly different. So, if I repeat this measurement of the value of g in my laboratory, I may consistently get a value which is either greater or less than 9.81, which is accepted as the correct value by many people. Most people will accept it as the correct value at the sea level and whatever. So, now the difference which I am getting between the measured value I am getting and the measured value, the value which is quoted by others, will refer to as the systematic error or it is the bias. So, whenever I measure, I am getting a different value. That means that my measurement has got some systematic errors in it, and if I look at the causes for this, and if I make a correction or make changes in the experimental setup, I may be able to reduce it or even eliminate. However, if I look at the random errors, I may make the measurement again and again. I will assume that the bias has been removed or reduced by suitable correction factors or correcting the instrument and so on. Still, every time I make the measurement, I will not get the same value. For example, the value of 9.81 is what I obtained or what is quoted. What I obtained may be slightly different from it. It may be sometimes slightly more, sometimes slightly less. It is not on one side. It cannot always be less or always be more, in which case we will talk about bias. If it is distributed over the correct value of 9.81 by small amount on either direction, either higher or lower, then we can say that the error is somewhat random. So, when the error is random, we can use characterize it by statistical means, and in order to do that, we look at two different quantities. One is the accuracy. The accuracy is good if the bias is small. That means, we say the smaller the bias, the more accurate the data. I will illustrate it with an example a little later. However, if I am looking at the random fluctuations, the smaller the random fluctuations with respect to the accepted value or a value which I can be confident about, then the smaller this random error, the more precise is the data. Therefore, the accuracy and precision refer to two different things. Let us take a typical example. The example I have in mind is something which is very familiar to all of us. Somebody is doing target practice. Maybe there are 2 or 3 different fellows. There are 3 examples shown here in this slide. The first example, you can see that each person has taken 7 shots, and in the case of the first fellow, all the 7 are within the first circle, the innermost circle. So, let us look at the second fellow. All his 7 shots have come very close to the edge of the target, and they are clustered in a corner. In this case, it is here in the center. In the second case, it is at the corner, and there is a third fellow whose shots have gone all over the big circle. They are not clustered, they are distributed throughout the thing. So, we can immediately come to the conclusion that if we remember what we described a little while ago about precision and accuracy, in the case of target practice, your idea is to hit at the target at the middle of the bull, at the very small circle at the middle. So, as far as this fellow is concerned, the first fellow, the precision is good, the accuracy is good because he has most of it are inside the first circle. That means that the value, if you assign, for example, I can do the following. I can assign a value of 10 for this circle, 9 for the next one, 8, 5, 4, etc. for the other circle. So, if you look at the score of the first fellow, it will be almost like 7 into 10, 70 he is going to get. So, if you look at the second fellow, he is also clustered in a corner, they are all good, but in the wrong place. He will probably get the lower score because 7 into maybe 5, 35, whereas this fellow got 70, he got only 35. Whereas this fellow is all over the place. He is not, his aim is very bad. So, accuracy is not good and precision is also not good because random fluctuation. With respect to the center of the circle here, you see that he is all over the place. So, an experiment can be like this. The first one, if you go back to the slide, an experiment can be like this. The value of G is 9.81 plus or minus very small value, or like this where it is all clustered at a corner, it is let us say 8.3 instead of 9.81, and there is this fellow is getting values of G, many sometimes it is low, sometimes high. So, there is no pattern to it. Therefore, you can see that these three examples are like examples for, one is for good precision, good accuracy, second one is for good precision, he is precise, but he is in that corner, accuracy is poor, and here is a case where it is neither precise nor accurate. Therefore, to summarize what we have been describing, we can generally say that experiments also are like this target practice. One would like to get the best possible value and the most accurate value, and also one must try to get the most precise value with the least amount of random errors. What we will do in the next lecture is to amplify on these, some of these things, try to characterize these quantities and look at a few examples for this. Thank you.